In this class, we will see about layout of sprinkler irrigation. In case of steep slopes, let us assume, in case of steep slopes, how laterals should be laid. See in this image, you are able to see the direction of the slope is from this place to this way. In this direction, the slope is downwards. As you see from the image, it is very steep slope. In these kind of situations, it is recommended that the laterals are laid along the contour or across the slope. See here, this is a sprinkler lateral and these are all the individual sprinklers, those are operating. Before we go further into this lecture, I would like to refresh your knowledge on interpreting contours. See here, this is an hillock. There are two hillocks, and for this hillock, if one does a topographic survey and draws contours, something similar to this contours you will get. If you look here, all the contours are closed, and the inner contours will have a higher value, and as you come out, the values of the contours or the elevations of the contours will keep coming down. So they should be recalled. And next thing is how to interpret a ridge and valley. See here in a topographic map, sometimes you will get this kind of patterns and these kind of patterns. Both appear similar, more or less. Both appear similar. Which one is ridge and which one is valley? You should know how to identify ridge and valley. See here, when you want to identify ridge or valley, what you should do is, let us say this is a section, and you should assume joining this way, joining the contour this way, next contour this way. If you assume joining that way, you will find that the inner contour is at a higher elevation and the outer contour is at a lower elevation. So this is similar to hillock. So this is a ridge line. See here, in this case, in case of valley, you see here if you close this way, okay, this close this way, and this is also closed this way. So in this case, you will find that this inner contour is at a lower elevation, and this is at a outer contour is at a higher elevation. So this is much similar to a valley. So this is a valley. So this has to be kept in mind for understanding this lecture. Next, we will see a case in which steep slope exists in an area. Steep slope exists, and the pump is at the center. So when pump is at the center, one can have a main line something like this laid, and from the main line one can have laterals this way. So this is a one option. Another option can be you can run your main line this way and laterals this way. Main along the contours and laterals along the slope. So if you do like that, what will happen? When your main line is operating this way, and laterals are, let us assume that you are operating a lateral this way, then it will be going on upslope. If it is steep, then it is not recommended. On this side also, it will run on a downslope. So if it is steep also, it is not recommended. So in this case, how the layout has been done is, if you look here, main line goes along the slope and laterals are along the contours. Okay, so this is a one kind of a layout one can adapt for steeper slopes. And you can also see one more important point here. The pump is at the center, and in this case, two laterals are simultaneously operated. So let us assume that these two laterals operate either on this side of pump or on the other side of the pump. In that case, both the lateral discharges will have to go through the main line. Instead, in this image, how the operation has been shown is one lateral is operating on the upper side and one lateral is operating on the downside. So what is the advantage of this kind of operation? So when you are designing your main, if you design for one lateral discharge alone, then it is enough. Then you will get a smaller pipe section, then it becomes economical. On the other side also, you will get a one lateral discharge design. So this kind of a operation and a design is called split line operation. Split line operation. You do not operate both the laterals simultaneously together, and you operate the laterals on either side of the pump, and because of that, the main size, main pipe designed size gets reduced, then it becomes economical. So we cannot say in all locations we may be able to design in this way. What is intended in this class is there are many options that will be discussed in each situation. When you visit field, then you should recall all the possibilities of the layouts and decide on for your situation how the layout design should be done. And this is another case. Here, if you look here, pump is uh, it is not at the center. It is at one boundary, and that too it is at the downstream. See here, this 175 contour, and the slope is this way. In this case, how the layout has been done, you see the main is running across the slope, and the laterals are going along the contour. In this case, three laterals are running. Okay, simultaneously, three laterals are being operated. So all these three laterals are operated at different locations simultaneously. If one can also think of operating all the three laterals at the same location. What is the advantage of operating three laterals operated at distant locations? It is operation becomes easy. Operation in the sense, especially shifting becomes very easy, because let us assume that all three laterals are simultaneously operated here. Then after the irrigation at this place is over, one has to shift the laterals from here to the adjoining place. So shifting becomes three laterals means the first lateral will move one lateral distance, one spacing, and the next lateral will have to move two lateral spacing, and the third lateral has to be moved for three lateral spacing. So this becomes a little difficult. And here, if you operate at a distant locations, as soon as one operation is over, it is moved to next location. Only one spacing only it gets moved. So these are all some of the things one should keep in mind when laying out. See, this is another situation in which no pump is used in cases of hilly areas. These kind of layouts are done. See here, this is the main line. This is the main line, and you get water. You get water through gravity only. You don't get pressurized water. What you do is you lay the lateral you along the slope, down slope. It is designed in such a way that the pressure lasts due to friction along the lateral is equated that is equated to the pressure that is gained because of the fall in elevation. So if that kind of a design is done, then that is a good design. One will be able to operate the sprinkler laterals without pump also. What you get is when you come down, your pressure gets increased because of the fall in elevation. So that pressure is used for operation of the sprinklers. So the friction last should be the pressure last due to friction. That should be along the way. That should be equated by the gain in pressure because of the fall in elevation. You see another situation. You see here. Look at the contours. Look at the contours. This is a the gradient is in this direction in this portion. And see here, these are all are shown as 80 contours. It means that this is a level length. Okay, so in this case, one gets here also no pump supply. The water comes by gravity. So in this area, the laterals are laid downslope, and as like previous case, the pressure gained due to elevation is used for operating of the sprinklers. And in this area, it is okay. In this area, it can be operated because you gain pressure because of the fall in elevation of the water. So if you come here, this is a level land. So when you are operating the lateral in this portion, then there will not be any fall in elevation when you come along this way. So for these kind of situations, have a booster pump. Booster pump. What does booster pump do? It adds pressure. It adds pressure when you are operating. When you are operating this area alone, operate this booster pump to get pressure and operate your sprinklers. So this is a one case. See here, this another situation in which look at the contours first. Look at the values of the contours and the shape of it. Look at the values of the contours and its shape. See here, this is a if you close this way, this is 100, 90. So this is a larger contour value at the center if you are closing something like this. So this is a ridge. This is a ridge. So this is a valley. This is a valley, and this is again a ridge. This is a ridge line. So in this kind of a situation, let us assume that you have a pump at the valley. Normally, most of the time, the pump will be at the valley because only in the valley your water source, your well will be located. So from there only you may have to pump the water to upper elevation. See here how the layout has been designed. See here and here it straight away goes to ridge. The main line straight away goes to ridge, and this is the main line. So from here, the laterals run this way. So the laterals run downslope. This is also going downslope, and this is also, if it is operated, this is also downslope. So here also this is also downslope. So it reaches valley. It does not. It does not again. It is not extended from here because if it is extended from here, then it will become again upslope. So that is not recommended. So this is a typical layout practice for ridges and valleys. See here another situation in which you have a, see here, this is a valley, right? This is a very big valley, and it is a depressed portion, and you have pump here. Okay, in this case, how the layout has been done, you see the main line, the main line, the main line goes this way, goes this way. This is the main line. Okay, from here the laterals are laid down slope. Similarly, on this direction, this is the main line, and the laterals are laid this way. So this is down slope, and it also does not go beyond this. See here, this is the depressed portion, most depressed portion until this it comes. So this is how this layout goes. So another kind of a case in which sometimes you may need to take water from an open channel. So in that kind of a situation, what one can do is, for every lateral one can have a some kind of a portable pump one can use. Portable pump can be used and lateral can be operated. Then shift the pump as well as lateral to the next nearby location and keep operating. So this is a one kind of a case, portable, lateral and pump. Another is portable laterals as well as main. See here, this is what is very much used in India. See here, this pump, and you have this. This is the main pipe, and these are all laterals. Okay, so you see here, all these are portable, laid over ground. The main is laid over ground, and laterals are operated. Once operation of this area is completed, total main and the lateral are shifted to the adjacent location, and it is operated. Here another thing is main. Main is buried. Main is buried. Main is buried, and laterals are operated, and laterals are movable and portable. This is what is the system what we have in Kumalur College. If you had recalled how the sprinklers in Kumalur College were operating, this is the situation. All mains would have been all mains had been buried, and all mains have been buried, and laterals are operated by shifting one after the other. So this is a much similar situation of our Kumalur College operation. And this is another complicated thing, much similar in the sense pump is at the center, your main, submain, both are buried. Main and submain both are buried, and the laterals are moved. So simultaneously, one can have many laterals operated at different locations. So this is another little complicated situation. And lastly, set system. Set system, see here, all are buried main, and your laterals, all laterals are fixed in place. All laterals are fixed in place, but it doesn't mean that all these laterals would be operated simultaneously. But one will not move one lateral after irrigation is done. All laterals, sprinklers, everything is fixed, and according to your pump capacity, either one or two or three or four or all can also be operated. So this is a very costly system, and this is called set system. So these are all the different kinds of typical layouts one must know. And this is not totally. You cannot say that this is all. When you really get into the field, when you look at different kinds of situations, you may have to think of different layouts, maybe mixture of all these things. So this lecture gives you a kind of a guideline for a starter. It's not, it doesn't make you expert in laying out sprinkler laterals. It comes by experience only. This is a formula which is very useful when one starts designing. And this formula by which one can find out what is the maximum area of land one can irrigate from a water source. How much can be the maximum land area? If you visit a field and let us say you look at a water source and you ask the farmer and what is the discharge rate that is possible from the water source, then he says 5 liters per second we can pump for 3 to 4 hours per day, and I want to lay the sprinkler system say for 10 hectares with that water. Then you must be able to find out whether that water is sufficient to irrigate say 10 hectares or 15 hectares. So you need to know, you need to balance what is the demand and what is the supply. So this formula does that. What this formula is very simple. On left hand side you see this is the demand, this is the evapotranspiration. This is called reference crop evapotranspiration that you would have studied in your irrigation drainage course. And I have also talked about this in your book in the basic session. In the basic sessions, these kinds of things are made available, because if you had not studied well, or if you don't want to go again and refer your earlier textbooks, here itself you can read it. So this is a reference crop evapotranspiration that comes in depth units, and this is a crop coefficient. If you multiply by crop coefficient and the reference crop evapotranspiration, you get the evapotranspiration per day, and A is the area. So area into depth you will get a volume. All these units have to be homogenized. If it is in mm and if this is in hectares, then all should be converted into meters or any convenient unit. So this is the demand and this is the supply. This is the supply. This is the discharge rate available. This is the discharge rate available from your pump, and this is the time of operation. This time of operation most of the time will be the number of hours of power available. So this is the thing, and this is the application efficiency with which you can apply water. And let us say in for sprinklers most of the time it is 80%, so 80 divided by 100.8, so that has to be substituted here. So most of the time you will be left with finding area. You will be finding area using this formula. So when you are using the same formula can also be used for drip irrigation also. For a drip irrigation system, the application efficiency is normally used as 90%. And for sprinkler irrigation, I said it is taken as 80%, because design is made in such a way it is 80 and 90%, and that is what is recommended by Government of India and international guidelines also. This is another useful simple formula. How many number of sprinklers one can operate at a time with a discharge of Q? So it is obviously, if Q is the discharge rate of your pump and small q is the one sprinkler discharge rate, then capital Q by small q will give you the number of sprinklers that can be operated simultaneously. So why I am introducing these simple formulas and all, when we design in the next class, all these formulas will be made use of. So next terminology is a representative area for one sprinkler. So look here, this is one sprinkler and this is the representative area for this sprinkler, so this is the same area as that of this. So if one wants to find out representative area of one sprinkler, this is actually the distance between the spacing of sprinklers along the lateral multiplied by spacing of lateral. So this multiplied by this distance will give you representative area for one sprinkler. Next terminology is set time. Set time per one lateral setting. In periodic move laterals, what is called set time per one lateral setting? So that is equal to this. This is one lateral. Okay, one lateral setting. Maybe in this case, two laterals are operated at a session. So set time per one lateral setting is the total time of irrigation at this place plus time needed for shifting to the adjacent location. So that is called set time. Set time is irrigation time as well as shifting time for one setting. That is called as set time per one lateral setting. Next terminology is pressure variation in lateral. Allowable pressure variation in a lateral. This is the design parameter, and based on this only design is made. Pressure variation. Let us assume that at the start of the lateral you have 25 meters of pressure head, and at the end of the lateral you have 22.5 meters of pressure head. So what is the difference? 25 minus 22.5 is 2.5. So the difference is 2.5. Let us assume that average pressure in this lateral is also 25. So the 2.5 is the difference divided by average pressure is 25. So that gives you around it's a case of 10%. 10%. 2.5 divided by 25. That gives 0.1, and that's a 10%. So like that, how much pressure variation in a lateral is allowed as per the recommendation is 20%. 20% variation is accepted. Above that, it's not accepted.